Physical interpretation of mode shapes. Today we will talk about physical interpretation of mode shape. Mode shape is a pattern of displacement that a structure assumes during its natural vibration. That means during the natural vibration, how the structure will displace. That pattern, that is called mode shape. Each mode corresponds to a specific natural frequency. So for each natural frequency, there will be one mode at which the structure vibrates freely. Okay. Cantilever beam. Cantilever beam is fixed at one end and free at other, making it particularly sensitive to the bending and torsional vibrations. So if you see, this cantilever beam is fixed at one end. Here this is fixed end and this is the free end, making it particularly sensitive to the bending. This is the bending mode I have drawn it. So here if you see this first mode, usually the deflection will be the bending will be the first mode. The first mode, n equal to 1, equation phi 1x, this is the mode shape, 1 by L. L if it is taken as the, say, 5 meters, from here to here it is the 5 meter L. So 1 by 5 into x, from 0 to 5 meter, 1 by L into x into L minus x. That is the first mode. The first mode shape, if you see, this is the shape of the first mode, the green color one, that is the shape of the first mode. That's the shape of the first mode. Is parabolic. This is basically parabolic. This x into x, this L minus x, x into L minus x, that will become like quadratic equation with maximum deflection occurring at the free end. You see, this is the free end, here is the maximum deflection occurs, and at the fixed end it is a 0. That's the first mode shape. This mode shape reflects the beam's most fundamental bending behavior. When the beam is excited, that is an impulse or dynamic load, this is the predominant response. So first response will be this bending one. This is the first fundamental response, fundamental bending behavior. The mass of the beam is most actively participating in this mode. Mass of the beam is most actively participating, making it a critical for structural analysis. Significance, if you see, the first mode governs how the beam will respond to most dynamic loads. Whatever the dynamic loads it comes, first mode it will become like this is the most dynamic behavior, such as wind or seismic activity or vibrations from machinery. Engineers typically focus this mode to ensure safety and performance. This is the fundamental mode. So this is the second mode shape, n equal to 2, phi 2 of x. This is this curve, 1 by L squared. Here 3x minus 3 by 2 x squared by L. Okay, this is also a quadratic equation, x squared. This mode shape has one node at point of 0 displacement, a point of 0 displacement. Here you see this one node, this node it has the point of 0 displacement located between the fixed end and free ends. This is the free end and this is the fixed end. Between these two ends, this point of 0 displacement is located. It features two peaks with maximum deflection at free end. Free end, it's a maximum displacement behavior. The second mode involves more complex bending compared to the first mode. Hence the beam bends in such a way that a section of it remains stationary while the ends move. This mode is significant in structures subjected to complex loading scenarios. The second mode is relevant in situations where dynamic loads, suppose if the external dynamic loads resonate with this particular frequency. It is important for understanding the vibrational characteristics of structures subjected to multiple loading scenarios. We can see third mode shape. Equation of this third mode shape, 1 by L cube phi x squared 4x cube 1 by 2x power 4 L squared. This mode has two nodes and it is characterized by more complex oscillations. Here you see two nodes. This beam exhibits 2 points of 0 deflection along its length. This is a point of 0 deflection, this is another point of 0 deflection along its length, which makes it more intricate vibrational pattern. In this mode, the portion of the beam move in opposite directions, indicating a more complex vibrational behavior. This mode shape becomes significant in structures where higher frequency of vibrations occur. Understanding the third mode is essential in advanced design situations, such as in case of high frequency loading. If the high frequency loading happens, this mode can get excited. or well multiple modes are excited simultaneously, which is common in mechanical systems. Alright team, today we are discussing about the first three mode shapes of this cantilever beam. Let's start with the fundamental concept. What is a mode shape? It's a pattern of how when the beam vibrates, pattern of deflection. Basically it's a pattern of deflection when the beam vibrates. That's what Chris is telling. Like exactly, the each mode corresponds to specific natural frequency. So each frequency has its own mode shape. The first mode is where the beam deflects most at the free end. And that's a crucial because first natural frequency typically determines how the structure responds to a dynamic loads. Can you give us the correct equation for the mode shape? Sure, for cantilever beam, the normalized first mode shape phi 1 of x can be expressed as phi 1 of x is square root of 3 by L by 2x minus x squared by L 0 to L. That's the reason. If you put L is the length of the beam, at the free end phi 1 of L is set as 1. So if our beam is 4 meters long, what does that look like? At x equals 0, let's calculate that. At x equals 0, phi 1 of 0 is 0. At x equal to 4 meters, that means phi 1 of 4 is 1. The maximum deflection occurs at the free end. So there is an important thing we need to note, like normalized first mode shape. There is a difference between first mode shape and normalized first mode shape. Sketching on the whiteboard, right? You get the shape peaking at the free end, and this represents the fundamental mode of vibration, essentially the first dance of the beam. If you see here, and this is the cantilever, and this is a fixed support, this is the free end. The first mode of vibration would look like this is a fixed end. This is the first mode of vibration. At the L, it becomes 1. This value becomes 1. It's normalized to 1. That's the first mode of vibration. Well put Rom. Moving to the second mode shape, phi 2 of x equals square root of 2 by L sine 2 pi x by L. How does that differ from the first mode? How does the second mode differ from the first mode? How does that differ from the first mode? Great question. The second mode has a node, meaning there's a point along the beam where there's no displacement. There is a node, meaning that there's a point along the beam, there's no displacement. It's a more complex, indicates how the beam can respond differently under various loads. So we can see that one as well. So if you see this second mode, there is a one point where it becomes zero displacement. Point along the beam, there's no displacement. So second mode shape will look like this way. This is the fixed portion. So this is the point. This is called node. Point where, meaning that there's a point along the beam, there's no displacement. This is the second mode of vibration. For example, let's calculate some values for the second mode. At x equals 0, phi of x equals 0. At x equals 2 meters, we see another peak, confirming the presence of node. At x equals 2 means this is the 2, x equals to 2 means half, 2 meter, becomes this peak, confirming there is a presence of another node. And for the third mode shape, phi of 3, it gets even more interesting. Phi of 3 square root of 2 by L into sine into 3 pi. Here 2 pi x by L, here 3 pi x by L. This must have two nodes, right? Yes, the third mode has two nodes and reflects more intricate pattern. That is crucial for understanding how high frequency vibrations behave. Let's draw this third mode as well. This is the cantilever beam. Let's draw the third mode, how it looks like. It means the third mode has two nodes. Two nodes meaning that there's a point along the beam, there's displacement is 0. So there are two nodes, here one node and here one node. The displacement pattern will look like this. It will come. Here it becomes 0 displacement and 0 slope. Here one node, here another node. That's the third mode shape. This is crucial for understanding high frequency vibrations, how they behave. Square root of 2 by L sine 2 pi x by L. Here square root of 2 pi L sine 3 pi x by L. So each of these modes is essential for analyzing the structural integrity of the beam under dynamic conditions. For example, if a load matches one of these natural frequencies, it could lead to resonance. If the external load matches with this one of these natural frequencies, it could lead to resonance, which we definitely want to avoid. That's why we have to consider all modes when designing. So we need to consider all modes when designing. Using simulation software, we can visualize these mode shapes and ensure the beam will perform safely. So understanding the mode shapes helps us predict how the beam will behave in real world scenarios like during earthquake or heavy machinery operation. And remember, the more complex the mode shape, the more intricate the response. Each mode contributes to our understanding of the beam's overall behavior. Thinking of it as a dance, each mode has its choreography. We need to ensure that all they work together without stepping on each other's toes. Now let's dive into some simulations to visualize these mode shapes in action. So in this example, we will see how the mode shapes positions happens. We can understand like it's a 4 meter length beam, so we will take x as the position is 4 meter length. Here is 4 meter. Along the 4 meter length, how the mode shape varies. This is the first mode shape. It maximum at this free end and 0 at this fixed end, and we can see this is the third mode shape. It has one node, two nodes, and this is the second mode shape. It has one node at this middle. So we can see how this varies. If we go to this here we can see L is the we will calculate a mode shape using this VBA macro. L as a double like length of the beam, I is integer, x is the distance, 5 1 2 3. So first L is the 4, that's the length of the cantilever beam, we are defining it, and number of points along the beam we are considering 100, and clear the content, existing content. So seeds one cells dot clear, it will clear all the contents, and seeds dot cells output row 1 dot value. So here we are putting this value as position 1, and then here we can see this is the output row 1. The output row is row 1 onwards, we are starting it. So 1 of 2 cells, 1 of 2 is mode shape 1, then mode shape 2, mode shape 3. Cells dot output row is we are considering as 1 after clearing it. Once we clear this seeds dot clear our cells, output row, it starts with the first row, starts output in the first row itself. Calculate the mode shape for I equals 0 to number of points. Number of points we consider is 100 points along the beam. X equal to 1 divided by L. L is the length divided by number of points. So L is 4 meter, 4 divided by 100. That points like a 0 0.04, 0.08, 0.12 like that. And then calculate the first mode shape. We have seen the first mode shape as 3 by L into x minus x squared divided by 2L. That's the first mode shape. And second mode shape, if you see here, second mode shape, this is square root of 2 by L into sine 2 into worksheet function pi x by L, 2 pi x by L. We have seen, right, this is sine 2 pi x by L or sine 3 pi x by L, square root of 2 by L into output row equal to output row plus 1. It should start like next row, it should give this output of x value, and this is the mode shape fill 1, fill 5 1, 5 2, 5 3. That's the next it has to add in the mode shape 1 1 2 3 automatically. So it starts with 0 to 100 points, and each 1 2 3 4 is the next columns. This is output row, this is the row 1 of 1. Here it becomes 2 of 1, 2 of 1 x value, then 2 of 2 first mode, 2 of 3 second mode. That's this value, the first mode, second mode, third mode, like this. This is the return. So seeds dot seed 1 dot cells output, next I, so it will be a loop. Then with the seats 1 dot columns a to d, it is like a auto fit, all these things we are modifying it. Then mode shape calculations are completed.